Let's solve Unit 8 Theory of Computation and Compilers questions. Consider the grammar. If I0 is equal to closure of S derives A with a dot operation, then how many items be in the set for GOTO? This question is taken from Syntax Analysis chapter, LR parser topic. So here we have something called closure and GOTO. So let's first understand what they are. For any set of items I, closure is formed in the following way. Initially closure is equal to I if A is equal to alpha dot B beta is in closure of I and B derives gamma is a production, then add B dot gamma to the closure and repeat. This is just a dot that is getting applied when parsing occurs. This is to say when there is a non-terminal and a dot occurs before the non-terminal, you have to take the non-terminal into consideration. So basically they will find the augmented grammar for this grammar. Augmented grammar is nothing but we'll just start with S dash derives S and from S we'll just go on. If we have S dash derived S, they will start with the dot operation here. It means you have to parse this particular S. Then this dot will be transferred to A. So for every non-terminal that gets a dot, that particular non-terminal's derivation should also have that dot operation applied there. So let's take I0 is equal to S derives dot A. This is what they have given here. When they have specified it as dot A, what does it include? What is in A? We have $B as one derivation for A and the other derivation is A derives ID. So this dot will be applied to both this production as well as this production. It will be applied to this dollar as well as to this ID. So whenever a dot is placed in front of a non-terminal, the production of that particular non-terminal will have the dot operation applied. So this is a process how LR parsing takes place. GOTO is nothing but we are performing a move. It means the parser will have two kinds of moves here. Either it can go to $B from A or it can go to ID from A. They are asking GOTO of dollar move. It means what happens when it moves this way. This is the question that is asked. If I is an item set and X is a grammar symbol, GOTO of I comma X is the closure of the set of items A derives alpha X dot beta, where A derives alpha dot X beta is in I. It means when I has A derives alpha dot X beta, what happens when you find GOTO of I comma X? This becomes A derives alpha, this dot will be shifting to the next symbol. So this will become X dot beta. So this is how we have to perform GOTO operation. Now they have told the GOTO operation has to be performed on this particular dollar symbol. Since they performed on X, the dot before the X moved to dot after the X. Here they have given GOTO is this particular production. So this is the value of I they have mentioned. Now we have to find the dollar part in GOTO. So where is the dollar here? It is here. In A it is present. Now we have to apply the dot. We will take the A production. We will just move the dot to the right side. So this will become $B dollar. So basically we had A derives $B dollar. Now since we use GOTO of this particular dollar symbol from I naught, what we do is we are just moving it to the right side. This makes it as A derives $B dollar. Just a movement of the dot operation. And what is the rule of the closure? Whenever the dot operation occurs to the non-terminal, the non-terminal's production should be added to the list. Basically, they gave only this particular production with the dot operation. Once we found that A is a non-terminal, what did we do? We included the production of A to this list. Similarly, the dot is now present in B. So what we should do is we should include the production of B. What is the production of B? The first production of B is B, comma A. The second production of B is A. We are just splitting it into two productions for easy applicability. The first statement will be B derives B, comma A, and we are placing the dot in front of B here. The next will be B derives dot A. So both these productions are applied. We have something called dot A here. A is again a non-terminal, which means we have to add $B and ID to the list again because a dot is placed in front of the non-terminal. So we are adding $B after the dot and we are adding ID here. Now the question is, how many items be in the set for GOTO? When we perform GOTO of I0, comma $, we end up with 5 items here. So this is the count of items they are asking here. It is 1, 2, 3, 4 and 5. Option number 3, 5 will be the right answer. Basically, we had only dot A. That's why we are bringing in the productions of A to this list. After bringing the production only, we are able to make this particular GOTO I0, comma $, move. When we apply this to the dollar, we are just moving it to the right of the dollar symbol. Since capital B is also a non-terminal, we are bringing in the productions of B first. When we place the dot before A, we are bringing the A productions next. This is why the order is like that. So initially we are applying it here. This part is converting to this first production here. For this part only we are applying the productions of B. For this part only we are applying the productions of A. Next question. Consider the grammar. Here X, Y, Z are terminals and capital T, capital Q, capital R, capital S are non-terminals. What will be the follow set of the non-terminal R? This question is from the topic syntax analysis again, but this time it is from top-down parsing in general. You have something called first set and follow set here. We'll just see what are they. First and follow allows us to choose which production to apply based on the next input symbol. First is a function that gives the set of terminals that begin the strings derived from the production rule. So when you have a production rule, you have to give the first set of terminals that come in the production. Follow of non-terminal is defined as the collection of terminal symbols that occur directly to the right of A. Right side means if there is a symbol A here, this will be the right side. This is called the right of A. Now we will try to find the first and follow of all the non-terminals. From that we will pick up the answer for follow set of non-terminal R alone. Let's take the non-terminals T, Q, R, S. Now let's take the first set. When we say T derives QX, the first symbol is a non-terminal. What should we do? We have to go and see in the non-terminal production, which is Q derives RS. From here there is a possibility of getting two values. One will be the terminal Y and another will be epsilon. So Q can have the first value Y as the terminal and epsilon as the value. What happens if Y is chosen? Y will be the first value. What happens if epsilon is chosen? If epsilon is chosen, this will be taken as epsilon S. It means you should not consider this epsilon, but you have to go and check S. What is there in S? There are two values, two symbols here. We have the terminal Z and epsilon again. So this part will also contain Z when R becomes epsilon. In case if T is given as T derives X, then this will be the first of T because it is the set of terminals that begin the strings derived from the production rule. But since there is a non-terminal given here, we are following these steps. So we are probing into Q, from Q we are probing into R. When R becomes epsilon, that case we are probing into S. So what are the possible terminals that we got? We got Y, we got Z, and we even got epsilon. So there are possibilities where R can be epsilon and S can be epsilon. But after that, do you have any other symbol here? We don't have any other symbol. Why are we not considering X? We have to consider the terminals that begin the strings. So in that case, we are stopping with Q alone. So the first of T will be Y, Z, epsilon. What about the first of Q? Whatever happened to T, the same thing will happen to Q because you are starting with R and S. When R becomes epsilon, S will take its place. So we have the same set of terminals for Q also. What about R? What is the first set of terminals that R can have? It can either have Y or epsilon. So we have placed them as it is. What about S? It can have Z or epsilon. We have placed as it is. Now how should we find the follow of a particular non-terminal? Place dollar in follow of S where S is the start symbol. If there is a production A derives alpha, B, beta, then everything in first of beta except epsilon is in follow of B. They have said it's a collection of terminal symbols that will occur directly to the right of A. This is with respect to follow of A. Now just apply follow of B with respect to alpha, B, beta. When it is follow of B, you have to take the terminal symbols that occur directly to the right of B. What is there in the right of B? It is beta. How should you take the set of terminals from beta? You have to take everything in first of beta. So when we have follow of R, we have to include whatever is in first of S. And this should be except the epsilon. So we are just giving minus epsilon. If there is a production A derives alpha B, or a production A derives alpha B beta where first of B contains epsilon, then everything in follow of A is in follow of B. You can consider this particular production as Q derives RS. This is going to be Q and this is going to be R. Now excluding the epsilon, we are including the first value of S, which is Z. So first of S is having Z and epsilon. Since epsilon is present, we are not including it in the follow set here. But since epsilon is present here, we are including everything in follow of A in follow of B. So what is follow of A here? You have to find the follow of Q. What is follow of Q? You have to go to the right side of the production. We have a production called T derives QX. For now, follow of A is this one and this will be the right of A. So here follow of Q means to the right of Q, what do you have? You have X. So this will be included here. If there is a production and the first of beta contains epsilon, so this case is true, then everything in follow of A, that is everything in follow of Q is in follow of R. So already we had Z here. Along with that, we are adding this X terminal also to the follow set of R. So this is how we will be finding the follow of a non-terminal. So for R, I have explained you in a detailed way because that is directly asked in the question. So which option is matching to this? Option number 3, Z, X will be the right answer. Now we will just find the follow of all the non-terminals for your learning purpose. Let's take T. T doesn't occur here. There is nothing right side to T. Initially they will place dollar. So this is dollar here. What about follow of Q? Next to Q you have something called X. And X is a terminal. So we are directly placing X. What about R? So the first step is we have to take the first of S minus epsilon. And since epsilon is present, you have to go with follow of Q. So first we'll have Z and follow of Q will have X. So this is ZX. What about S here? S doesn't have anything in the right side. They have given two options here. If there is a production of this form or a production of this form, then include the follow of A in follow of B. It means include the follow of Q in follow of S. So this can be equated to A derives alpha B. Now whatever is in follow of A should be there in follow of B. So whatever is in follow of Q should be in follow of S. So follow of S will have only X here. So this is how we have to find the first and follow of the non-terminals. Next question. If L1 and L2 are context-free languages, which of the following is true about L1 intersection L2? Regular languages is a subset of context-free. They are a subset of context-sensitive. They are in turn a subset of recursively enumerable languages. When you are going to have intersection of two CFL, they can never result in regular. So this is false. CFL is closed under union, concatenation and clean closure, but not closed under complementation and intersection, which states that intersection of CFL and CFL will never be a context-free language. So option 1 is also ruled out. Now the question is between whether it is recursively enumerable or context sensitive. Definitely when there is intersection that is not closed, we will go to the immediate previous level context sensitive. But the option is included as recursively enumerable also. Recursively enumerable set includes all languages for which there exists a Turing machine that will halt and accept any string in the language. The intersection of two CFLs falls into this category because a Turing machine can be constructed to enumerate all strings in both context-free languages and accept those that are in the intersection. When you are going to implement regular language, finite automata comes into existence. For CFL, we have PDA, DPDA. Similarly, for context sensitive, we have something called linear bounded automata. For recursively enumerable, we have something called Turing machine. This Turing machine has the capability of implementing all the other three languages because they are subsets. That's why they say when there is intersection of two CFLs, they ultimately fall into the category of recursively enumerable because Turing machine can be constructed for this purpose. What about context sensitive? It is actually more restrictive than recursively enumerable languages. While some intersections of CFLs might be context sensitive, it is not guaranteed for all cases. There are cases where intersection of CFL may be context sensitive, but it is not true for all the cases. It is not guaranteed in the sense it is definitely a part of recursively enumerable languages, but it is always not a part of context sensitive language. This is why we are ruling out even option number 4. We are going with option number 3. L1 intersection L2 is recursively enumerable as the right answer. The intersection of two CFLs is always recursively enumerable, but not necessarily context sensitive is the main point that you have to consider. Next question. Arrange the following stages of a Turing machine operation in the correct order as they occur during computation. The Turing machine starts with an infinite tape divided into cells. Infinite means you don't have any end to the tape. The machine reads the symbol in the current cell under the head. So the first process is reading the symbol. We can mark C to be the first process. So all the options start with C. Based on the current state and the symbol read, the machine refers to its transition function to determine the next actions. This is C, and this line can be equated to transitioning to a new state based on the current state and symbol read. So this part comes next, and this will be point D. So what are the next set of actions? Writing a symbol in the current cell. which may be the same or different from the one that is read. So this point is available in A, moving the head one cell to the left or right. So this is moving the tape head left to right, and here it is B. Changing to a new state will be another set of action. The machine stops its operation when it reaches a predefined halting state. The contents of the tape at this point represent the output of the computation. The remaining one is halting and accepting or rejecting the input. So it will halt, but it will either accept or reject the input is the overall scenario here, which will be the final step. So this can be equated to E here. Option number 3 will be the right answer. So they have given C and E as the initial and the final steps for all the options. All you need to work out is with A, B and D. Next question. Arrange the following stages of parsing in the correct order as they typically occur in the compilation process. We are starting with lexical analysis. This will be A. Then we have syntax analysis, that is C. Then we have semantic analysis, which is B. Then we have intermediate code generation, it is D. And we have code optimization, which is E. So the order is A, C, B, D, E. Option number 2 will be the right answer. Next question. Arrange the following language classes in ascending order according to their expressive power as defined by Chomsky hierarchy. We are starting with type 3 regular grammar, then type 2 context free grammar, type 1 context sensitive grammar, type 0 as unrestricted grammar. So when we say unrestricted grammar, it will have the highest power there. So the option should end with D. Only 2 options are ending with D. So we will rule out the other 2. So this will be D, unrestricted grammar. Then we have context sensitive languages or grammar. This will be B. Then we have context free grammar, which is A. Then we have regular grammar, which is C. Which has the least expressive power here? Of course it is regular grammar. Here we have something called unrestricted grammar, which will have large amount of expressive power. So we have to start with C. Only one option out of these 2 is starting with C. So we can rule out even 3. We'll go with option number 1 in this order since they are asking in ascending order. Next question. Which of the following are context free language? When we want to find whether a particular language is CFL or not, we will always go with the pumping lemma rule. But here we are not getting into the pumping lemma part. We have W power I, X power J, Y power K, Z power L in all the 5 options. So let's take A first. We have a condition called I plus K is equal to J plus L. W I, X, J, Y power K and Z power L. I plus K means the number of W's and Y's together will be equal to the number of X and Z's together. We usually use push down automata to count whether number of A's are equal to number of B's. In this PDA stack allows comparison of only 2 variables at a time. We have to see whether we are able to use only 2 variables to check all these conditions. So first let's start with the first condition, I plus K is equal to J plus L. What does this actually mean? We can say I is greater than or equal to J or I is less than J. Now we will take an example. We will go with I is equal to 2, K is equal to 3. Then we will go with J is equal to 4, L is equal to 1. So ultimately I plus K equal to J plus L will give you 5. So let's take the string actually. W power 2 will give 2W. Then J, X power J is X power 4. So we have 4 number of X. Then we have 3 number of Y because it is Y power 3. Then L is only 1. So Z is only 1. Let's understand how this can be done using a PDA. Whenever you read W, you just push into a stack. So let's take a stack like this. So the first symbol is red now. And we have another W. So we are also pushing it to the stack. Read X. If W is in top of the stack, pop W. If the stack is empty, push X. When we read the first X, we are checking whether W is there on the top of the stack. Yes, W is there. So what we should do? We have to pop W. So we will pop it out for the first X. Now we will again read X. Is there a W in the stack? Yes, when this W goes on, this W becomes the top of the stack. We are also taking the second W. So which is available in the top of the stack, we are removing that also. Now we still have X here. If stack is empty, they are asking to push X. So we will go for a fresh stack again. Now we are pushing X. So the first X is pushed here. The second X is pushed here. Now what is in the top of the stack? This X is in the top of the stack. Now we are reading Y. If X is in the top of stack, pop X. Else you have to push Y. So for first Y, we are popping out X. For the second Y, we are popping out the other X. Now when there is no X, what you should do? You have to push Y. So this time we are just pushing Y. What about the next? Read, it is for Z. If W or Y is in top of stack, pop it. For one Z, we are just popping out this Y alone. Is the stack empty now? Yes, it is empty. Yes means this particular string is accepted. No means the string is rejected. So here the stack is empty finally. So this string is accepted here. It means I plus k is equal to j plus l is true here. That's why the string is accepted. Here we have checked this for I that is less than j. Now we have to check for I is greater than or equal to j. We will have I is equal to 3, k is equal to 2, j is equal to 1 and l is equal to 4. We are swapping the values of I and k and j and l. Now just check I and j. 3 is greater than 1. We will even check for this condition whether this particular mechanism is working. We are taking the stack here. We will once again have the input symbol here. W, W, W. It's for 3 i's. Then we have only 1 j, that is for x. Then we have 2 y's and 4 number of z. For w's, we have to push it to the stack. For 3 w's, we will push 3 w's onto the stack. Now we are actually reading x. So for 1x, we are popping out 1w. Now we will get on to y. If x is in top of stack, you have to pop x. Otherwise, you have to push y. You have 2 w's here. You don't have any x here. If there is no x, what you should do? You have to push y. So we are pushing both the y's here. Now for reading z, what is the condition? You should check if w or y is in top of stack and then pop them out. So for the first z, this y will go. For the second z, this y will go. For the third z, this w will go. For the fourth z, this w will go. So this is the same stack only. Above these 2 w, I am adding 2 y's. Is the stack empty now? Yes, it is empty. It means this string is also accepted. I plus k is equal to 5. J plus l is also equal to 5. Which of the following are context free? Since PDA is accepting this particular string, we can say A is a CFL. When you find A is a CFL, you can rule out the other 3 options and mark option 1 A comma B as the right answer. From this, what do we understand is B is definitely a CFL. C, D and E are not CFL. Now we will get into B. What is the condition for B? I is equal to J and K is equal to L. It means the number of W should be equal to X and number of Y should be equal to Z. Whenever you have W, you have to push it. When you find X, you have to pop W. Similarly, whenever you have Y, push Y to the stack. When there is Z, pop Y out of the stack. So here we have checked for 2 strings. We'll just place those 2 strings here. Let's get into I is equal to J and K is equal to L. So whenever we read W, we push W to the stack. When we read X, we pop W. When we read Y, we push Y. When we read Z, we pop Y. So let's take an example. I is equal to J is equal to 2. And k is equal to L is equal to 3. So we'll have WWXX, then we'll have YYYZZZ. So this is the sample string we are going to take. So I is equal to j is equal to 2 and k is equal to L is equal to 3. So this will be WWXX YYYZZZ. So just go with the stack. When we have W, we have to push it. So we have pushed 2 W's. When there are 2X, it will be popped. Again, when we go for Y, we have 3 Y's for every Y here. Then for every Z, we are popping out all the 3 Y's. We are checking whether the stack is empty at the end of input. Yes, it is empty. It means the string is accepted, and this is also a CFL. So B is quite easy to prove, but once you find B is right, you have to check either A or C. So in this case, if you understand A, it will be easy for you. B is definitely a CFL. So the answer that we marked is also right. Now how do we prove that C, D and E are not CFL? Here we have something called I is equal to J is equal to K and K is not equal to L. When I say I is equal to 2, J is equal to 2, K is equal to 2 and L is equal to 3, L is not equal to I as well as J. This is somewhere similar to A power n, B power n, C power n and D power m. You can check A power n, B power n in PDA. But when you want to check 3 variables, whether they are equal or not, because this first condition is to check whether these 3 variables are equal. If that is the case, one PDA will not be enough. So we can conclude here itself that it is not context free. So here we can say W, X, Y and we'll have 2Z. How do we prove that W is equal to X is equal to Y? So when you want to combine all these 4 variables together, this is quite not possible. So in that case, we are actually going with not CFL with respect to C. What about D? I is equal to J is equal to K plus L. Here we can have I is equal to 2, J is equal to 2, K plus L is also equal to 2. WWXX then YZ. You can compare up to 2 variables here using PDA, but when you want to take account of third and fourth variable and equate it to this particular variable, that cannot be done using a single push down automata. Maybe we need 2 stack. It doesn't come under the category of context free languages. So this can also be taken as not CFL. What about E? This is also similar to C condition. 3 variables are equal here. So W will be equal to X and it will be equal to Z. But they are not equal to the count of Y. So here also we can conclude they are not CFL. If you go with finding the pumping lemma of all languages, you may not always arrive at the right answer because it is about the selection of this VXY. If you don't select it appropriately, even the right one will give you the wrong answer and even the wrong answer will become right for you. Next question. Which of the following languages are recognized by non-deterministic finite automata NFA but cannot be recognized by deterministic finite automata DFA? This question is actually a wrong question, we can say, and that's why they have dropped this question. We'll first understand what is wrong. A language is recognized by a deterministic finite automata if and only if there is a non-deterministic finite automata. In other words, we can say for every DFA there is an NFA and for every NFA there is DFA possible. When we have some kind of regular expression or regular grammar, we will try to find the non-finite automata implementation first and from there we will try to convert it to DFA. So every DFA will have an equivalent NFA and every NFA will have equivalent DFA. So there is no difference in the power of NFAs and DFAs. When every NFA recognized language can be expressed by a DFA, this question becomes meaningless. Now let's check whether we are able to solve it using NFA or DFA. L1 is actually the length of W is even. You have to find whether the string is of even length or not. For even, how we can check is, it can start with 0 or 1, it can end with 0 or 1. Whatever comes in between should be a combination of two characters. So we can keep it as 0 0 or 0 1 or 1 0 or 1 1 with clean closure. Just pick 0 here, 0 here. 0 0 is even length? Yes. Just pick 1 here and 1 here. 1 1 is even? Yes. When you try to pick 0 0 in between and add to the first two zeros, this becomes 4 number of zeros, it is again even. So definitely A can be expressed in the form of regular language. So it can be implemented by NFA as well as DFA. Now what about B? The length of the string is odd, they have given. So how do we check for odd? We will do the same thing. We'll go with 0 or 1 in the starting, and then we will also go with the two character string here, and we'll stop here. We start with 0 and we don't have any number from this particular expression. This is odd length. We start with 0, then we have two zeros from here. So this becomes a count of 3. It is again odd length. So this is also expressed in regular expression format. So B can also be implemented using DFA and NFA. Let's take C. All zeros come before all ones. If that is the case, we'll first have zeros and then we'll have 1. This is how we'll be expressing it. And what about E? All ones must come before all zeros. So first we'll have 1 and then we'll have 0. If it is star, 0 occurrence is fine. When it is plus, at least one occurrence should be there. Only when one occurrence is there, we can confirm that zeros can come before 1. So that's why we have made it as plus symbol. So even C and E are expressed using DFA and NFA. What about D? W contains an equal number of zeros and ones. This cannot be implemented in a regular language. It is not possible to generate a regular expression for the language. Equal number of zeros and ones can be checked using pushdown automata, and this is a context-free language. So whenever you have 0, you push it. Whenever you have 1, you pop the 0. This is how we'll be doing. This 0 power n, 1 power n is similar to A power n, B power n, which can be proved using a PDA. So this is definitely a CFL. Now we have understood about this question. We know why the question is meaningless, and we know 4 of the options can be implemented using NFA as well as DFA. So A, B, C, E, all the 4 can be implemented using NFA and DFA. Why is D not possible? Because you need to count the number. You have to know the number of zeros in order to check it with the number of ones to tell whether they are in equal count or not. So that's why we are not putting it under regular language category. Now, what should have been the actual question? There is a possibility of changing this question. There are CFLs that are recognized by NPDAs that cannot be recognized by DPDAs. There are certain context-free languages that can be recognized by non-deterministic pushdown automata, but that cannot be recognized by deterministic pushdown automata. If we can change this question as which languages can be recognized by NPDA and cannot be recognized by DPDA will make sense. This applies to pushdown automata but not to finite automata. This question is possible. NPDAs are more powerful than DPDAs. Now the next work is, we will try to apply all the 5 options and check whether we will be able to implement it using NPDA or DPDA. Let's take A and B. It is about the even length and odd length. The language of strings over 0, 1 with an odd or even length is a regular language. When it is a regular language, it can be recognized by DPDA itself. So if you take the finite automata, that can be recognized by DPDA. When DPDA cannot recognize something, it requires some additional work, then it goes to NPDA. When something is recognizable by NFA or DFA, it can be recognized by DPDA itself. We need not go to NPDA because they say NPDAs are more powerful. So in this case, this can be recognized by DPDA. What about C and E? They say all zeros come before 1 and all ones come before 0. This can be recognized by DFA or NFA again. So DPDA is more than enough to recognize this particular language. What about D? W contains an equal number of zeros and ones. This can be recognized by a NPDA but not by a DPDA because it cannot handle the non-determinism required to match the number of zeros and ones. If we change the question as which of the following language can be recognized by NPDA and not by DPDA, we can mark option D as the right answer. Only D needs NPDA and it cannot be done by DPDA. The rest of the options A, B, C, E can be recognized by DPDA because they are recognized by NFAs and DFAs. Next question. Which of the following properties correctly describe a regular grammar? Let's check the statements. All production rules are of the form A derives X B or A derives X, where A and B are non-terminal symbols and X is a terminal symbol. A grammar is said to be right linear if all productions are of the form A derives XB or A derives X. A grammar is said to be left linear if all the productions are of the form A derives BX or A derives X. So this is possible and this is also possible. So A is definitely true. 2 and 3 can be ruled out at this stage itself. So from this what we can understand is a regular grammar is one that is either right linear or left linear. That's why we are marking A to be right. Now let's get on to the B statement. Regular grammars are more powerful than context-free grammars and can express any type of language. Unrestricted grammar has the most expressive part. So when they say regular grammars are more powerful, that is actually wrong because regular grammar is a subset to context-free grammar. CFGs are more powerful than regular grammars, you can say, and they have given can express any type of language. This particular capability is given only by unrestricted grammar. Regular grammars are the least powerful here or least expressive here. So this statement is totally false. When we rule out B, option number 1 also gets ruled out. Option number 4 will be the right answer. There is a direct correspondence between regular grammar and finite automata. Yes, any regular language string or the string that are generated using the regular grammar will be accepted by finite automata. It can be non-deterministic finite automata or deterministic finite automata. So both NFA and DFA can be considered here. Regular grammar's implementation part is finite automata. It is absolutely true. That's why we are marking A and C as true here. What is wrong with D then? Regular grammars can generate languages that are not recognized by any type of automata. This is also false. Regular grammar is the most restricted grammar. That's why you cannot solve all the problems using regular language. In that case, this type 0 grammar will be able to solve any of its subsets. Next question. Which of the following tasks could be attained using syntax trees in compiler design? Actually, when you see the phases of compiler design, syntax tree comes after syntax analysis. For which phases we can use them? We can use for semantic analysis. The same syntax tree can be used for intermediate code generation, and it goes on. So after the generation of syntax trees, these phases are possible. Type checking is done in semantic analysis phase. Code generation is done in intermediate code generation phase. Code optimization can also be taken as the next step of intermediate representation here. Syntax tree can be used for the following tasks. So we can include type checking, code generation and code optimization as the tasks. Option number 1, A, B, C only will be the right answer. What about error handling? Error handling in compiler design occurs throughout multiple phases. Now we will see how they occur in different phases. In lexical analysis phase, they detect lexical errors such as invalid tokens or characters that do not match any pattern defined by the language grammar. So this is like identifying an illegal character in the source code. So whatever is given in the parenthesis is just an example of one such error. The syntax analysis phase throws errors like the sequence of tokens does not conform to the language grammar rules. Say for example, if there is some missing semicolon or unmatched parenthesis in the code, they come under syntax analysis error. What about semantic analysis phase? This identifies semantic errors where the syntax is correct but the meaning is not valid. Using an undeclared variable or type mismatches come under this category. What about the next phase? This ensures that the intermediate code adheres to the language semantics. This is detecting error in the translation of high-level constructs to intermediate representation. What about the code optimization phase? Although less common, some errors related to optimization strategies can be detected here. What kind of error you can identify? Unreachable code or redundant operation can be detected here. What about code generation phase? This ensures that the final machine code is correctly generated. Detecting errors in the allocation of registers or incorrect instruction formats can be the errors detected during this phase. Each phase has its own strategies for error detection, reporting and recovery to help developers identify and fix issues efficiently. So far I have just told what kind of errors can be detected. So this is to tell you that error handling will occur at all phases. Linking and loading stage handles errors related to linking multiple object files and loading them into memory. So this is like missing external symbols or address resolution issues. Errors can occur even in linking and loading stage. With this we are completing Unit 8 solutions.